Good afternoon, folks. How are you today? Our next topic is curve fitting. This is probably something you're going to utilize in many courses. So I hope you learn it well and would be able to use it in your other courses. So we are given n data points. What we mean by it? We are given their coordinates. So we'll number the points I from 1 to n, and their coordinates are xi, yi. And what we want to do is we want to fit a linearized fitting function. That means we want to fit a curve y, which is a function of xi. We'll just make it function of xi, which is c1 times some function 1 of xi. So once we know xi, we can evaluate this function times c2, another function, and so on. So we have k such terms. Actually, let's make it m such terms. So we know these functions, f1, f2. So we know f1, f2, on and on to fm are known. So this kind of is a long form. So let's write it in a short form. Y at xi, which again we will shorten it to yi, is sum of many terms. Each term has a constant, let's call it Cj, times a corresponding function Fj, which we evaluate at xi. And these terms, which are numbered from 1 to m. What we want to find then is best values of the unknowns C1 through Cm. So therefore we have m unknowns. So we have n data points and m unknowns. So we need to define what we mean by best. So let's visualize. This is our x. This is our y. So we have these data points. So I is equal to 1, 2, 3, so on. So what we want to do is we want to fit, say, a straight line. So what we mean by best is that our straight line for this set of points should be unique. No other line can be better than this. Also, it should be best fitting in the sense that it should minimize deviations from the data point. So it should be a good fitting line. It should be very far away. So let's again look how we can write this algebra using matrices. So we had y was some constant times some function at xi. where j goes from 1 to m. So of course, the order of multiplication is not important. Algebraically, we could write this down as fj xi times cj from j1 to m. So this y, we can collect all of them and form a vector. So we could call y1, y2, y3, it'll go all the way to yn. So this matrix would be yn by 1. So let's see what is y1. Y1 is f1 at x1 I have to get my sizing right to give you the visualization. So f1 times c1, f2 times c2, on and on and on to fm times cm, right? Then we'll do the same thing for y2. It'll be f1 at x2, f2 at x2, on and on and on, fm at x2. So it'll be f1 times c1, f2 times c2 correspondingly. And finally, we'll have f1 xn to fm xn. So this is our F matrix, which has n rows and m columns. And of course, this is our coefficient matrix, m rows, 1 column. So you see that we have written this entire set of equations. We have n equations, remember, in this very compact matrix form. So let's talk about what do we mean by deviations. So remember, our criteria was that our curve should be unique and minimize deviations. So let's say we have these points, we fitted our straight line. So of course, some points don't fall on the straight line. They deviate from the straight line. So we can define deviation in several forms. We can divide deviations in terms of this x. We can define deviation in terms of y. We can also define deviation which is perpendicular. So we define deviation if our x's are certain. So if only x has uncertainty, we should use horizontal deviation. If y has uncertainty, we will use perpendicular vertical deviation. If both x and y have uncertainty, we will use perpendicular deviation. Typically, what we have is our x variable is a control variable, so it does not have any uncertainty. So the only uncertainty is in the y variable. So what we are going to do is we are going to use this as our deviation. So we choose vertical deviation because only y values have uncertainty. That's what we have assumed. So we will define this deviation as curve value minus the data value. So this is curve value minus the data value. Okay. Next question is how many data points do we need? So we are asking the question n versus m. So this is number of data points. This is number of unknown coefficient. The C's that are in our fitting function. So let's see, suppose we want to fit a straight line. So if we want to fit a straight line, we'll say y is C1 times F1x plus C2 times F2x. So here we'll make F1 to be 1, F2 to be x. So we will have equation of a straight line. So therefore we have two unknowns, m is equal to 2. So suppose if we have only one point, we know that many lines would be best. Any line passing through this point would be best. So our result will not be unique. So when n is equal to 1 less than m, result is not unique. So of course we can't have only one data points with two unknowns. Okay, let's try 2 points. So now n is equal to m. Now of course our best straight line will pass through every point. So curve passes through every point. Okay, third is we might have say 3 points, and our best straight line might be this. So n is greater than n, curve may not pass through any point, yet it might be the best. Right? So our key idea is therefore that n should be greater than equal to m. It cannot be less than m, because otherwise our result would be not unique. All right, so we want to minimize deviations. So we want to minimize deviations. So let's see in what form. So let's choose our first criteria. So what we do is we say we minimize sum of deviation. So what is total deviation? Sum of EI from 1 to n, right? So if we have a curve, we have these points, we take these vertical distances along with their sign and add them up. So let's see what a problem this has. So if we have 2 points, we want to fit a straight line. We know the best straight line would be passing through both these points. This is the best straight line. So let's just imagine the center point between these two. Now, if we draw any line passing through the center point, notice if this deviation, remember this is our line. So when line is above the point, positive deviation. So let's say this is positive 5 points. And this will be therefore negative 5 points. So the best straight line, sum of deviation is 0. Any line that passes through the center point, deviation is equal to 0. So of course, this is not a good criteria, therefore. So the problem was we paid attention to the sign of the deviation. So let's use criteria number 2. This time we will minimize the sum of magnitude of deviation. So that way the deviations will cancel out. So now let's consider another scenario. Let's consider, for instance, we had two pairs of points, one here and one here. So obviously the best straight line intuitively we know is we pick up the midpoints of these two and the line passing through will be our best straight line. So let's see what is the sum of deviations here. Let's say this is 2 units, this is 2 units, this is 5 units, this is 5 units. Remember, we are not paying attention to sign of the deviation anymore. So our total deviation would be 2 plus 2 plus 5 plus 5 is 40. Now let's draw another line. Let's suppose I draw a line connecting this point to this point. Obviously, intuitively not the best, but you can see total deviation would be 4 plus this 10. So this line, dashed line, also has the same deviation, 14. So any line that I can draw between these two dotted lines, as I've shown in the slide, will have a deviation that will total up to 14. So again, we won't get unique results. Okay, let's try another criteria. This time, let us try to minimize the largest deviation. So if we take our E vector, we minimize the infinite norm. So this is also called minimax criteria. We are minimizing the max norm. So what would our line be? X, Y. So suppose we have 4 points which fit perfectly on our straight line, and one point is an outlier. So ideally what we would say is we would ignore this point and we will fit a straight line to these 4 points. That would be our best. But what this criteria does, since it minimizes the maximum distance, it is going to fit a straight line and say the best straight line is this one. So that all of these distances are the same. So they are all 5. So that would be the best straight line in this case. Even though it gives undue influence to this outlier, this line still is best in that sense, and it is unique. You'll find we can fit unique curves this way. So this is a valid criteria, even though it does not fit our intuition. But this kind of a technique is used in quality control. So we are not going to use this criteria. But let's look at the next criteria. So in the next criteria, we are going to minimize the sum of squares of deviation. So we are going to sum all the deviation squares. This way, if they are positive or negative, doesn't matter, they get squared, the sign gets squared. And this is called the least squares criteria. Remember that this basically means we are taking Euclidean norm and squaring it. So it is same as minimizing the Euclidean norm of our deviation, vertical deviation. So when we do so, what happens is, even if we have small deviation, as you will see here on the left, we get a line that fits our sense of good fitting line. And even if we have large deviations, even for the scattered data points, this line looks to be the best fitting straight line. So it doesn't matter if the deviations are large or small. This criteria provides unique and to us best fitting straight line, best fitting for our sense of deviations. Okay, so our goal is therefore what we are going to do is we are going to minimize sum of EI square with respect to C1, C2, Cn, right? So how do we minimize things? We take the derivative. So we are going to take derivative of this EI square with respect to Cj and set it equal to 0. And we'll do this for each unknown. So when we do so, we will end up with m equations, and of course we have m unknowns, right? So let's differentiate this. So when we differentiate, so notice this is just our point number, so it has nothing to do with unknown number. So we can move this derivative inside. So when we take derivative of this, we will get 2ei del ei del Cj, right? Equal to 0. So let's look at each of these. So what is EI? Remember, EI was our deviation, is the y value on the curve minus y value of the data point, right? Well, y value, we remember we did, this was C1 times F1 plus C2 times F2, and I wrote it in matrix form, but let's say we just, for the time being, write it in this algebraic form. So we are summing up m terms minus yi, right? So now let's take derivative. Let's see what derivative looks like. So this one, remember, would look like f1 x1 times c1 plus f2 x1 times c2 and so on and so forth, right? So that's what it is. We can make these i's. All right, so when we take derivative with respect to some c, what will happen? Let's suppose it's a C1. Suppose we are taking derivative with respect to C1. There is no other term which contains C1 except this. So this one be F1 xi. So if we are taking with respect to Cj, our derivative would be Fj xi, right? So we go back. Our equation, remember, was that we wanted to set 2ei del Cj is equal to 0. So let's substitute that. So we have m such equations, remember. We can throw away 2. Also, I want to just change the order of these because I want to write it eventually in a matrix form. So we just saw del ei del Cj is Fj. So we'll get Fj xi times ei equal to 0. Again, j1 to m. This is being summed for every point, remember. Let's expand ei. Remember, ei was yi minus little yi, right? So we can separate these out. So I can write Fj xi times yi, I1 to n. And this times this, I'm going to put on the other side. So equal to Fj xi times little yi, I1 to n. Okay. So let's look at just one equation for, so this is one equation, right? J1 to n. So let's look at what it will look like for one equation. So our equation, remember, is Fj xi big yi, I1 to n, equal to Fj xi times little yi, I1 to n. Okay. Let's look at this guy. Yi, remember when we began it, we wrote yi was Fj xi times Cj. Right? It was yi was just C1 times F1, C2 times F2 plus C3 times F3 like that. Now in matrix form, remember we wrote this as, we wrote y, which was n by 1, was function matrix n by m times c m by 1. So what we are going to do is we are going to take this and substitute it here. So when we do this, our matrix form will become like this. This Fj, this matrix will look like F transpose. So the left side would look like F transpose times yi. Yi is F times C is, remember, F transpose times y. Let's make sure all our sizes are okay. So this was n by m. This is m by 1. If it is n by m, its transpose would be m by n. So m by n, and this is n by 1. So remember, we know all the y data points. We know all the function values. So we know all of these. We want to find c. That's our problem. When we multiply these two, we'll get a matrix A, which is m by m times c m by 1. And when we multiply these two, we will get b m by 1. And of course, since we know both, we can multiply. We know both, we can multiply. And this is our typical linear system. We know how to solve this. So typically on a computer, we are going to take inverse of A and multiply it by B. Okay, so let's do an example. Before we do an example, let's again remember our problem. So we are given n data points. That means we are given xi and yi, I from 1 to n. We are also given a fitting function. And our fitting function is y as a function of x is c1 times f1 of x, c2 times f2 of x, and on to m. So therefore we know f1 through fm. We know all these functions. And what we want to find are best values for c1, c2, cn, right? That's our problem. And our method says all we do is we set up a function matrix, which is n by m, take its transpose, which is m by n. So this will be our matrix A, times C is F transpose, which is m by n, times Y, which is n by 1, right? So we are going to find C. That's our problem, okay? So let's say we are given 4 data points. Let's say as on our example, n is equal to 4. So we are given xi, yi. X is 1, 2, 3, 4. And y is 2, 4, 6, 7. Okay. And we want to fit a straight line. So we want to fit y is equal to c1 times 1 plus c2 times x. Okay. So our first fitting function is 1, right? This 1. Second fitting function is x. So this is just 1. This is 1, 2, 3, 4, same as x. So notice now this matrix is our y matrix, 4 by 1. This matrix is our f matrix, 4 by 2, right? So let's take f transpose. Actually, I'm going to write this on a fresh paper. So our y matrix is 2, 4, 6, 7. And our f matrix is 1, 1, 1, 1, 1, 2, 3, 4. So our F transpose matrix would be 1, 1, 1, 1, 1, 2, 3, 4. So when we do matrix A, which is F transpose times F, we will get 2 by 2 matrix. So we do 1, 1, 1 times 1, 1, 1, add them together, we'll get 4. We do 1, 1, 1 times 1, 2, 3, 4, we'll get 1 plus 2 plus 3 plus 4. 1, 2, 3, 4 times 1, 1, 1, we will get 1 plus 2 plus 3 plus 4, 10. And then we will get 1 square plus 2 square plus 3 square plus 4 square, right? So we will get 30. Let's look at matrix B, F transpose times Y. Okay, so we are going to do F transpose times Y. So we'll 1, 1, 1, 1 times 2, 4, 6, 7. So we'll get 2 plus 4, 6, 6, 12 plus 7, 19. Then we'll do 1 times 2 plus 2 times 4 plus 3 times 6 plus 4 times 7. And we are going to get 56. So if we are using a spreadsheet, we can take A inverse like I have done here. Then A inverse times B, we'll get C. So we get A inverse using spreadsheet 1.5 minus 0.5 minus 0.5, 0.2. And we multiply B by it. So multiply this, we will get C, which is 0.5 and 1.7. So our best fitting line is y is equal to 0.5 plus 1.7x. Right? We can plot it. So let's see. So here the blue dots are our data points and our red dots are the uppercase Y, the data points on the curve. I fitted the straight line and you can see it's a well-fitting straight line. There is one point I must make here, that this matrix A is always symmetric. So that is a good test that you have done your math right. So in this case, remember this is always symmetric, this product. Okay.